In this video, we'll learn about a new addition to frequentist inference proposed by the philosopher Deborah Mayo and her collaborator Aris Spanos. That is an attempt to fix some of the proposed objections to frequentist inference that we've discussed in previous lessons. And as a way to try to frame this addition to frequentist inference, which is called severity, we'll look at, sort of remind ourselves about these two fallacies that can arise in standard frequentist inference. So one was the fallacy of acceptance. This was basically the idea that if you conduct a hypothesis test that does not produce a p-value less than a given threshold, and you have no evidence against the null hypothesis, then if you claim that you have evidence for the null hypothesis, you'd be committing a fallacy. So that has to do with this language around failing to reject the null hypothesis versus accepting the null hypothesis. It's a fallacy to do the latter. So that's one fallacy, and Mayo and Spanos claim that they have a way to build up some evidence for a null hypothesis, but it requires this additional notion of severity that we'll learn about. The other fallacy is the fallacy of rejection. So this one says that evidence against the null hypothesis can be misinterpreted as evidence for a particular alternative hypothesis. And that particular alternative is important. When you reject a null hypothesis, you are claiming evidence for a composite alternative, meaning sort of infinitely many values that sit underneath the alternative hypothesis. Just think of a null hypothesis where some mean is equal to 0 and the alternative that the mean is greater than 0. Greater than 0 encompasses infinitely many real numbers. But it's not clear what you have evidence for other than that your parameter sits in the interval greater than 0. So again, Mayo and Spanos have a methodology that could provide evidence for specific alternatives, whereas standard frequentist inference doesn't give you that kind of information. So I've got two different visuals of how you might conduct inference under the frequentist paradigm. One is the classical frequentist inference, and what I mean by that is basically frequentist inference before Mayo and Spanos, the notion of having a hypothesis test where you reject or fail to reject based on a p-value being lower than some threshold. And then the bottom, the error statistical philosophy, this is the philosophy developed by Mayo and Spanos that incorporates the notion of severity that would allow you, according to them, to make specific evidential inferences for particular alternatives or corroborating the null hypothesis. So classical frequentist inference, some say, is behavioral in the sense that if you have evidence that rejects the null hypothesis, that points towards the alternative, the correct interpretation of that is that you should behave as if the alternative is true. And that behave might seem a little bit odd, but it's actually kind of required for the interpretation in the sense that, remember, frequentist inference does not place a probability value on the alternative or some sub-alternative or any hypothesis for that matter. So it doesn't give you reasons to believe with a particular probability value some alternative. What it really does is say that you might behave as if the alternative is true. So classical frequentist inference is very empirical in that sense. It's about what you might actually do based on observations, not about strength of belief in some alternative. So evidence points towards the alternative in the sense that you might make decisions as if some alternative is true. Now, the error statistical philosophy that has this additional severity criterion that we will explore soon, developed by Mayo and Spanos, this gives an evidential interpretation to that rejection of the null hypothesis. Here, evidence points towards the alternative hypothesis if you have a low p-value for your test. And Mayo and Spanos claim that here you can calculate a severity score. So this will be a probability of something measured on the interval 0 to 1 for different discrepancies of at least gamma from the null hypothesis. So basically what they're attempting to do is provide a number that gives the strength of evidence for various deviations from the null hypothesis. And if you think back to a prior lesson on Lindley's paradox, this could be helpful in kind of solving or making sense of Lindley's paradox, because we can look at different deviations or different discrepancies from the null hypothesis, and some of those deviations will be very well supported and others won't be. So if you have a really large sample size, thinking back to Lindley's paradox, it took a very small deviation from the null in your sample to reject the null hypothesis. But maybe the severity score for a large deviation from the null will be very small, which means that you don't have evidence for a large deviation from the null. You really only have evidence for very small deviations from the null. That seems like it would be helpful if severity would give us that kind of evidential score. And in fact, it does. We'll see when we actually compute severity scores that if you have a huge sample size, smaller deviations from the null will have a higher evidential score in terms of severity, and larger deviations from the null will have a much smaller severity. So there's a similar way of interpreting the error statistical philosophy if you get a large p-value and you fail to reject the null hypothesis. So in the classical frequentist inference, kind of prior to Mayo and Spanos, if you have evidence, I mean, this is a bit of a abuse of notation here, evidence that points towards the null in the sense that it produced a large p-value that did not reject the null. You failed to reject the null hypothesis, and there's always this question of what does that mean? Well, I think classically it means you could behave as if the null hypothesis is true. It's not something you built up evidence against. Now, Mayo and Spanos think that they have a way of, in some sense, corroborating a null hypothesis in the sense of, again, producing a score on 0 to 1 that would measure the strength of the evidence for various discrepancies less than gamma from the null hypothesis. So suppose you had a p-value that was large and you're sort of pointing back towards the null, you fail to reject it. You might have a severity score that is quite high for small gamma and quite low for large gamma, which would suggest that your deviation from the null hypothesis is very small, and maybe it's so small that you're sort of corroborating the null rather than doing anything out far into the alternative. And Mayo and Spanos are really motivated by a sense of objectivity in statistical inference. They really think that getting it right, meaning that there is some truth out there, that the parameter is sort of in the null hypothesis or very, very close to it, or it's out in the alternative. And it's really important for us to try to get that right, for our test to reflect the reality of the situation. And not just worry about ensuring internal consistency. That's a bit of a jab at Bayesians, because Bayesians really think about consistency, right? Probabilities being internally consistent as a way of getting at truth. Mayo and Spanos think that's not enough. Internal consistency is not enough. What we really need to do is get it right in the sense of point towards the objective reality, and our test should reflect that objective reality. So they really care about objectivity and orienting ourselves towards the world. And they think that frequentist hypothesis testing does that very well, especially with their added layer to this paradigm of severity, right? Trying to corroborate null hypotheses, but also build up evidence for specific alternatives, whether those alternatives are very far from the null or small deviations from the null. So it's sort of a summary of some key points of this error statistical philosophy, this frequentist inference that has this additional layer of philosophical support through this notion of severity. It's evidential rather than behavioral. We saw that moments ago when we talked about the interpretation of rejecting or failing to reject the null hypothesis. The classical frequentists were behavioral. Mayo and Spanos think they have an evidential interpretation in the sense that they provide a severity score that points towards specific hypotheses. We just mentioned they have a commitment to objectivity and getting it right. They really think that statistics is not just about, updating probabilities based on prior beliefs, but it's an active process of coming up with a severe test. This test that is meant to get at the truth and is meant to really distinguish between various hypotheses. And of course, the kind of test that we've done in a previous lesson where we p-hack our way to scientific glory, for example, is not really an active inquiry in the way that Mayo and Spanos are suggesting. Sure, it was active in that we chose different ways of operationalizing variables in order to get a result that we want. But what Mayo and Spanos believe is an active way of doing statistics is really figuring out what is the right kind of test to distinguish between some null situation, a null hypothesis, and some real deviation from that. How can we actually distinguish between those two and corroborate a null so that we can build up evidence for it and make decisions based on that, or point towards some specific alternative and then act as if that's true. And then the notion of severity, which again we will define more clearly philosophically in just a moment, and then we'll work on some activities where we actually operationalize severity and implement it on specific hypothesis tests in a future lesson. So severity is helping us answer the question, when do data provide good evidence for or a good test of a hypothesis? Severity is meant to answer that question. So Mayo and Spanos basically have two severity principles. One is a weak severity principle, and the other one is a strong severity principle. And so here we'll just look at the conceptual statement of these principles, and then in a future lesson we'll look at how to actually compute a severity score for particular tests. So the weak severity principle says that one does not have evidence for a hypothesis if nothing has been done to rule out ways in which that hypothesis may be false. So if data agree with the hypothesis, but the method used is practically guaranteed to find such agreement and has little capability of finding flaws with H, even if they exist, then we have bad evidence, no test. So you could imagine a situation here where maybe you've p-hacked or somebody has p-hacked and you produce a small p-value pointing in the direction of some alternative. But Mayo and Spanos want to say you actually haven't severely tested the hypothesis that you're pointing towards, this alternative hypothesis, if you've p-hacked your way to it, because your method was practically guaranteed to find agreement with this alternative hypothesis. You manipulated variables, maybe removed some data points. You've done a lot to point towards that alternative. So you haven't done much to try to rule it out. And so in that case, your test has bad evidence, and it's not really a test, right? It's not a severe test in their language. So the strong severity principle states that we have evidence for a hypothesis H, just to the extent that it survives a stringent scrutiny. So if the hypothesis H passes a test that was highly capable of finding flaws or discrepancies from H, and yet none or few have been found, then the passing result, that evidence, is evidence for the alternative. And basically what Mayo and Spanos are trying to say here is that you really need a severe test. You need something that would actually differentiate between these various hypotheses in order to say that your result is robust or will stand up to scrutiny. So one scenario that you might think of here is, imagine you get a p-value that's relatively large, and you compute a severity score, and the severity score seems to show that a small deviation from the null hypothesis, some very small gamma, has a high severity score, then you might claim, yeah, we do have evidence for the null hypothesis because a very small deviation is highly evidential, right? It has a high severity score. And again, we'll practice with these kinds of calculations with real tests in future lessons.